Okay, hi everyone. Welcome to this week's lecture, and thanks again for letting me record this one. So I've decided we're going to go with the sorting algorithms this week, and then when we're back in person next week, we'll get onto the informed searching algorithms for AI. So this week is just going to again be a little bit more of a recap of some algorithms you've seen, maybe one or two that aren't super familiar, but we're going to just be going through their complexity and a little bit more of the foundational analysis. Okay. So once again, sorting is when you're given a list of numbers and you arrange them in ascending order. Descending or ascending is probably arbitrary. So for just consistency, we're going to look at ascending order in this lecture. So we're going to start off by looking at the first three, which are brute force approaches. That's the max sort, the selection sort, and the bubble sort. You will see that the max sort and the selection sort are pretty similar. Then we'll look at the decrease and conquer sort, which is insertion sort, and then a divide and conquer method, which is merge sort and quick sort. Those names seem fairly, or descriptions seem fairly kind of arbitrary. You'll see that there's some property of the algorithms themselves, but in general, we're trying to move from the searches that are a little bit more manual. They just kind of operate on the same data structure, trying to move around the values to the different indices to algorithms which treat subproblems, and so that's where the kind of conquer or divide and conquer comes from, or you're just kind of decreasing the scope of the problem each time, which is then the insertion sort. Alright, so let's look at the selection sort. There's a GIF here at the bottom. So all the selection sort is going to do is try and scan over the numbers and then find the appropriate place to put a digit into the list. Okay, so you're going to start at the first position, and so this is on the outer loop. Then you're going to scan the remaining list and find the smallest value in the list, and that's then the inner part of the loop. So the outer part determines which index is being updated. The inner part scans through and looks for the appropriate value to put in that index. And then you're just going to swap the current value with that smallest value you find at the end of the inner loop. Then you're going to move on to the next index and repeat. Okay, and so every time you move on to the next index, you obviously don't go back and start changing earlier indices which now have the correct value. So in a second or two, this GIF should restart. We can look at it again. So it starts off by saying it should go into index 0, which currently has 5. So you're going to scan through the rest of the list. And you're going to try and find the minimum value. Alright, so it found 2. Now it found 1, so it updates where the minimum is. It got to the end and it says, well, okay, the 1 was the minimum value, so that needs to go into index 0. Now it moves over to the next index. Index 1 has 2 in it. It scans, it gets to the end, and it sees that there are no minimum values, so it just moves forward. And then it sees 4 in the next index. It gets to 3, figures out that 3 is less than 4, that's my new minimum, and it swaps. Okay. The max sort is similar, it just has a opposite outer loop to the selection sort. So you're going to find the max value and place it at the end and then repeat. Okay, so the same kind of idea, but we can look at the algorithm 1 for the max sort instead of just looking at the example. As you can see on line 1, you start from index I, and that starts from n minus 1, right? So the last index in the list, and it goes down to item 1. The reason it doesn't go down to index 0, it goes down to index 1. The reason it doesn't go down to index 0 is, by definition, an array of size 1 would be sorted, and so when there's one index left, so index 0, then it would already be sorted, so there's no reason to keep the algorithm going any longer. Okay, so by assumption, the algorithm is given a list and it has size n, where my list is an array with n entries, okay, index 0 to n minus 1. And then the output of the algorithm is going to be my list again, but now where the values in my list are sorted. Okay, so you know that index 0 is going to have a smaller value than index 1 and 2, and so on, up to n minus 1, which is where the max value will be. Okay, so you start on line 1, you're going to cycle down from the largest digit, where the largest digit should go, the largest value should go, which is the last index. And you're going to cycle down to 1, you go into line 2, you're going to look for where the max is. Okay, so initially you just set it to the index you're updating. So you say start by saying what is the current or at least what's the position I'm updating. So by default, you just aren't going to change the list because the value in max pos will stay the same unless you update it down here. Okay, and then you're going to say for j from 0 to I minus 1, so you're still going to loop from left to right, kind of arbitrary, you don't have to, but at least you're going to do a scan over all of the indices in the list and try and find the maximum value. If you find an index that currently has a value that is larger than what you think the maximum is, alright, so you go into my list, you look in the maximum position, you get its value, which will be the max. If my list in index j is currently larger than that value, then you just update where you think your max value is to be j. Alright, and you keep looking. So this would be different if we were doing the insertion sort. You would just start from 0 and go up to n minus 2, I guess. Okay, and so then at the end of the loop, you get to, of the inner loop, you get to the end, you know where the maximum is, and so now you're going to just swap the values that are in max pos and my list I, and so you know that now the value that holds the max in that sublist is going to go into index I, which is the correct place to put it. Okay, so you've now gone and put the appropriate value in max in the index you cared about, which was index I. Okay, let's look at the properties of selection and max sort. So are they complete? Yes, both algorithms will sort the list and return the sorted list. Considering the complexity, so each time we move a value to the right place, we have to check minus one of the unsorted list size, so just one less than the unsorted list. So comparing all other values to the one that is already there. We do this for all n positions, although a list of size 1 is already sorted, so the last outer loop doesn't do much. Okay, so like I said earlier, especially on this algorithm in the last slide, you saw you won't loop down to index 0, you just stop at 1. On top of that, you always then just, in your internal loop as well, you're just always going to loop over the other values, right? So you initialize to where the index is that you care about, and then you look at all the values that remain in the unsorted list. Okay, you can see where this is going at the end. The number of comparisons then is you start by doing n minus 1, at least n minus 2, then n minus 2, you go all the way down, and you'll eventually get to that sequence, alright, where it's now a sum of values from 1 up to n minus 1, okay, which gives us this equation at the bottom that we've derived. And so we know how to get that. It's just n times n minus 1 divided by 2. And so you end up at roughly order n squared. Okay, depending on how you actually describe the algorithm, you may get a constant changing out front here, in which case this may be n minus 1 and that becomes n minus 2, or so on. But ultimately the derivation will stay the same whether or not you count the comparison at the current index or so on. And so you still always end up with order n squared for these two algorithms. Okay, and so to illustrate the broader point of that we've been making in this class, which is the fact that our analysis depends on the metric we choose, we're going to try and consider how complexity would change if we do use another metric. Alright, so let's see how best and worst case would compare. So if you're counting comparisons, both sorting algorithms deliberately move the correct value to each index. Alright, and so this is independent of the instantiation of the problem. It's just scanning over, finding the value you're looking for, the max remaining value in terms of max sort, and then moving it into the appropriate position. Okay, and so both algorithms search through the full remaining unsorted part of the list, independent of the instantiation of the problem. So what I'm trying to say here with these 2 points is that the outer loop doesn't depend on the problem, and the inner loop doesn't depend on the instantiation of the problem. And so both algorithms have no unique best or worst case instantiation when you're counting the number of comparisons, right? It's just always order n squared, like we saw on the previous slide. However, if we change how we count to just counting the number of swaps we have to make, then for argument's sake, let's say that we update line 7 on that algorithm so that we only swap if max pos and I are different indices, alright? So we're not, if max pos is unchanged, we're not going to make the swap, we're just going to move forward. So you can just put let's go all the way back. We're just going to put an if statement here, right? So we're not going to do swap max pos list I if max pos is just the same as what it was initialized to. We're just going to kind of check that it actually went into this inner loop here. Alright, so we can say if max pos is still equal to I, then obviously that swap does nothing, so then you don't do it. Okay, in which case, instead of then considering the number of comparisons happening here, which is how we did our initial count, right? And we were saying that this loop over here doesn't depend on the instantiation of the problem. This loop doesn't depend on the instantiation of the problem. And so we get a consistent number of counts out here. This part, the swaps, may actually change depending on the problem, right? This operation now has a meaning, especially if we're going to do an if statement that says check max pos is not equal to I first. So for argument's sake, let's consider how this changes our complexity analysis. Okay, damn it, I put it in here. Alright, so we're changing line 7. Okay, in that case, we would then have a condition which can give different best and worst case complexity analysis, and this would also work for a selection sort. This is bad. Okay, so in the worst case, if the original list is in descending order, then every run of the outer loop will find a smaller value that needs to be swapped. Okay, so every time we're moving through this list, we're going to start off with the kind of maximum value, or sorry, the final index, so where we want to put the maximum value. But if the list is already in descending order, we know that the smallest value in the sublist that's unsorted will actually be at this index I. And so when I scan over this, index 0 is going to find a really large value, the largest remaining value, and so I'm always going to end up swapping kind of the remaining index up into the current position, right? Obviously, once we kind of keep going now, the smaller values where it needs to go, but so on. Okay, and so we're always going to be scanning over numbers that are where we're going to find a smaller value, and the maximum value is always going to have to be swapped into position. Okay, and that's because the list is reverse sorted. So in that case, there's always a swap to be done, which gives us the worst case. But in the best case, if the original list is already in ascending order, then the lowest value will always already be in its right place. Right? And similarly, if you're doing max sort, then you can always have the maximum position in the right place. And so then no swaps will ever be needed. So the whole point here that I'm trying to make is if we're then counting the swaps, right, you can then get a case where the reverse sorted list requires always us to move the values around. There's always a swap at the end of the outer loop, or at the end of the inner loop. And in the best case, everything's already where it needs to be, and so no swaps are needed. Okay. Alright, so as I said, then max.sort will be looking for the maximum value in the outer loop to sort into ascending order. So it's a very similar selection. In this case, the worst case is if the original list is still in descending order, then every run of the outer loop will find the max value at the start of the list and have to swap it to the end. Best case, if the original list is already in ascending order, same story. Okay, so which metric is better then, right? So if we're counting swaps, which again is not the usual way of doing this analysis, we can get best and worst case complexities for the algorithm, which may be useful for describing inconsistent performance if it's ever used in practice, right? So if you're ever doing some kind of sorting algorithm and you're maybe using one of these two and you're getting inconsistencies, perhaps maybe there's something going on in terms of how that function is calling the swap, or how the instantiation of the swap function is being used, or a similar idea where you're doing a bit of work inside of the loops and you kind of can start to see that how you count the units of work will show you where the discrepancies are. Okay, so perhaps this is better. However, counting comparisons is actually closer to the actual number of lines of code that get run by the algorithm, right? Because the swaps completely ignores that internal loop, right? Where a lot of the actual code coverage is sitting. So you're going to be doing the comparison line of code many, many times over before you see the swap line of code once. Okay? And so the benefit here is that counting comparisons is closer to actually counting the number of lines of code that actually get run by the algorithm. So counting comparisons considers the operations used by the inner loop, so swaps only occur in the outer loop, so less code coverage in a sense. And so the point here that I'm trying to make isn't which is better, but the fact that you should be able to at least argue for the merits of both, right? Kind of comparisons, the standard one, we're going to only kind of look at the complexity in the Friday tutorials. If we get around to any of these sorting algorithms, we're only going to look at their complexities when we're counting comparisons. I'm not going to do the counting the swaps version of it, which is also why I'm not kind of getting too into the details of the best and worst case there. The point is that they exist, right? And so you should be able to consider when you may want one property of a metric from another. For example, sometimes you may want to have a best and worst case complexity. In another case, you may want it to be a little bit more closer to the code coverage. And in this case, I think counting the comparisons shows something pretty fundamental about this algorithm. In the big scheme of things, kind of maybe just ignoring whether or not you have to run this one additional line of code to do a swap or not. You know, that function of swapping is not an expensive operation, so maybe it's not the one we really care to track, even though it can be a slight difference. In that case, counting comparisons describes something a little bit more fundamental about the algorithm, which is the fact that it actually does roughly the same amount of work, regardless of whether or not the input is different or what the instantiation of that input is. Okay, so I think it's important that this metric is actually describing that fact about the algorithm. If this is the only thing we're looking at here, if obviously that swap function is a lot more complicated than I'm saying at the moment, then obviously maybe we do want to count it. And then in that case, the best and worst case complexity for that sub module, that sub function, is what matters. Okay. Lastly, let's think about optimality. So let's stick to counting comparisons for these algorithms. So we know that both algorithms are correct. So they satisfy the first property of optimality. But do they ever do more work than necessary in their worst cases? Well, we've just said they don't have a worst case. All right. Again, I'm assuming we're sticking to the counting comparisons here. So the question then just becomes, well, do they ever do more work than necessary? And the answer is yes. All right. So you can sort a list more efficiently in general, and we'll see one of the algorithms just now that does so. Okay. So in this case, because we know that there is an algorithm that can do have a lower bound on its worst case, it means that selection and max source are not optimal. Okay, and so in that case, just for a proof, I guess, all you would have to do is just say, well, here's the instantiation of a better algorithm that has a lower worst case upper bound, and so it's now these algorithms are therefore not optimal. Alright, so they are both not optimal. Okay, let's move on to bubble sort. I know that those two sorts are pretty basic and kind of old hats, but again, I think I'm trying to get across some concepts and make sure we're just defining things properly as we go along, so that when we do these things a little bit more rigorously and on a Friday session, it's not a completely new wave of information. But we can start getting into some of the kind of more interesting algorithms. So bubble sort. Okay, so instead of swapping one element each time in the outer loop, what we're going to do is we're going to just do a bunch of swaps as we scan through on the inner loop. Okay, so that's the first big difference here, is that we're still trying in an outer loop to get the correct value into a particular index, and we're still going to do each index one at a time. But while we're working on the inner loop, we're going to use the time we have and use those operations to also just do some swaps to try and get things into the right order as we go along. Okay, so here's the pseudocode. Same start as the last time, so we're going to take in a my list of size n, and we're going to output that same list, but now with sorted values. So looking at line 1, so you're going to start from index I, which starts at the maximum value, so that where the maximum value should go, so the last index in the list, and it goes back down to index 1. Okay, same story, you don't have to go down to index 0. And so for j from 0 to I minus 1, so then you're going to loop all the way up to index I, so all the way up to where you want to put the correct value. And as you loop, you're just going to check whether or not index j, so again the index of the inner loop, so as you're scanning across the list, you're just going to check whether or not that index and the index to its right, if index j is larger than the index to its right, you're then just going to swap them. Okay, and you can see how this works. We're currently trying to get the largest value into index I, so where the largest unsorted part of the sublist should go. And so as we go along, we're just going to keep looking for cases when we find a number that's bigger than its neighbor, and then we pull it across. Importantly, when j increments, so let's say that we did find a case where j is bigger than j plus 1, and so we swap them, that larger value is now in index j plus 1, right, due to the swap. And so when this inner loop carries on, it's j plus 1, and so you're actually looking at the same value a second time, which means that you can now carry this large value all the way up. Alright? And so if you're not necessarily looking at the largest value the whole time in the sublist, you will eventually kind of leave this number behind. So let's say you're looking at the second largest value in the list, so 5, and that was from the start all the way on the left. You will then pull it quite far up the list by iteratively doing these swaps, and so then you actually find the largest number value, and then this condition will fail, and you'll start carrying the largest value up the list, and then by definition this will keep looping until it's in the right spot. But that's helped us later on, because while we were doing the earlier scans, we got a lot of those early swaps out the way. Alright, and so you're just constantly making use of the information you have while you're scanning through looking for that max value. And then you know that by the end of this kind of cycle of swappings, you'll eventually put the maximum value towards the end of the list. Okay, so here's an example. Alright, so you compared 1 and 5, or 5 and 1, 5 bigger than 1, so you swapped it. Now 5 is not bigger than 6, 6 is not bigger than 7, 7 is bigger than its neighbor 2, so you're going to swap them. Okay, then you move over, you're still looking at 7 compared to its neighbor, which is 4, you swap them. And so now you've got 7 into its correct index. Okay, so 8 was already in its correct position, so you were only considering the sublist to the left of 8, and so 7 is now in its maximum position. Okay, now you encounter a lot of the earlier values which you sorted on the previous loop, and so you can scan over 5 and 6. 6 swaps with 2, scan over 6 swaps with 4. Okay, you can already see the sublist on the left is starting to emerge as well, so 1, 3, and 5 are relatively ordered, and so on. And you're just going to keep going. In this case, it's going to now pull 5 into its right position. Okay, and then lastly, we're just going to have to now actually end up pulling 3 into its correct place. There we go. And you should be starting to see something interesting emerge here, which is the fact that if I've ordered all the numbers to the left already, it should become easy because there will be no swaps. So there's this really, really elegant kind of detection that just happened here, where if you can scan through all of them without making one swap, then you must already be able to tell that it's sorted. Okay, so what are the properties of a bubble sort? Is it complete? Yes, it will get us a list that is sorted. What is the complexity in terms of comparisons? So by default, there are no cases to consider. The algorithm just moves the max value to the end of the unsorted part of the list each time. So in this case, still no best and worst case. It just does the normal comparison number of comparisons every time, which is order n squared, best and worst case. So that's because it has this inner loop and an outer loop. So again, the outer loop is getting the value to the outer loop is getting the appropriate value into each index. Alright, so because I've said each index, that's the loop over n, and then within getting the correct value into each index, it has to do a scan as well. Alright, so that scan, that's doing the swaps on the inside. So you have the inner loop scanning through and getting the value to its right place, and then the outer loop doing that for all of the different values, which gives us n squared. However, we can make a clever change to the algorithm, which is the one I preempted on the previous slide, which is the fact that if you scan through and you see that you've done no swaps on one full scan, then we know that we've actually put the list already into order. So if we do one full outer loop without making a swap, then it means that the list is already sorted, so we can break out of the loop early. Okay, so you've gone into the outer loop once for a particular index, and so now you're going to loop over all the values on the internal loop. And so if you do no swaps on that one pass, then you know that you've now already got the list in its correct order, and so there's no reason to keep going. There's no reason to then actually keep doing all of the different outer loop passes because you know that the list is sorted. And so you can break out, and now we have a best case scenario, right? Which is the fact that this would be the case when our outer loop needs no swaps from the very start. In case your first outer loop needs no swaps, and so this would only happen when the list is already in ascending order, which is great. So if you don't make this breakout modification, you would just run the algorithm normally. But if you just make this really clever check, which says if no swaps in the previous iteration, then the list is already sorted. It means that you now have a condition that you can check. And so in this case, if you just get given a list in ascending order, it would take one sweep of that array just to check that it's already in order, and then you can stop. So we just do one scan of the list to see that there are no swaps, which requires ordering. Okay, and so then in optimality, similar to selection and max sort, bubble sort is correct and does not have a specific worst case. Alright, so it does have this breakout on the max. It does have this breakout on the best case that we saw on the previous slide. But again, optimality is done by comparing worst case, the bounds on the worst case. And so, bubble sort isn't sensitive to a particular instantiation for the worst case. It just always does that order n number of scans. Okay, and it does, however, do more work than is necessary, and so it's order n squared. Again, there's in the next set of algorithms there will be one that is optimal. Okay, so it is correct. That satisfies the first property, but it doesn't have the lowest bound on its worst case complexity, and so it's not optimal. Okay, so here's what we've done. So again, we're trying to just recap here. So we're given a list of numbers and we're arranging them in ascending order. The brute force versions that we've looked at, we've all done them. None of them are optimal. They're all correct though, and they all have some interesting complexity, but we are looking for an algorithm now that is going to give us something optimal. Okay. And so we're now going to look at the decrease and conquer algorithm. So in this case, you're going to exploit the relationship between the solution to a single instance of the problem and then a solution to a smaller instance of the same problem. So again, can you break up the problem into smaller and smaller instances and still use the small instance to solve the bigger one? And then for divide and conquer, we're just going to literally split the problem into independent subproblems, and then you solve the subproblems and combine them to get back to the solution. Alright, so let's get started on insertion sort. Okay, so in this case, you're going to maintain a sorted sublist. Alright, so there's a little bit of memory usage here. And so for every new value, you're going to insert it into its correct location into that sorted sublist. After each insertion, the sublist grows by 1, but it always maintains the sorted order as you go. Alright, so this is known as being loop invariant. So there's this rule that will never change no matter how many times we loop over it, which is the fact that the sublist stays sorted. Okay, and so this is going to be correct by design. It's got this kind of induction design to it by nature. The proof of correctness and stuff that we'll go into for this actually uses induction. So by definition, a one element array is always going to be sorted. And then as we add elements, we always know the sublist is sorted, and so all we care about is the one value you need to insert. Okay, so you can almost then say, regardless of how many we've inserted before, up to size n, we know that's going to be sorted, so then therefore can I just say something about n plus 1, and then you'll just prove the complexity that for that last number you're inserting, it will go into its correct place and keep the sublist sorted. And then you've now done that with induction. So that's the whole point, is that every time you loop, you finish in a state where you have a sorted sublist. Okay, and so once the new value is in, the sublist is sorted for the next insertion, and you can keep going. So let's look at the full example of this. So we have our sorted sublist in green, it just currently has the number 5 in it, and we want to insert the value 3. So we're going to look into our list and say, where should 3 go? Well, it can go to the left of 5, and so we're just going to go and slot it in there. Then we're going to move over, and we're going to say, well, now I need to put 7 into the correct place, and so can I get my sorted sublist on the left with 7 in it? Okay, and so it's already in its correct place. We leave it. For 1, it just needs to move over 3 times. It gets put in its correct place. 10 is where it should be, 11 is where it should be. 2 needs to go over 5 times, and then 14 is where it needs to be. So therefore you have your entire sorted list. Okay, so here is the algorithm. You input my list in the size of size n again, and then you need to output the list in sorted order. Okay, so you're going to start from index 1 to n minus 1. Again, you don't need to start at 0 because the list of length 1 is already sorted, so you just start by saying index 0 is my sorted sublist, quotes. Okay, and say x is the current value I want to move into its right place, and then j goes up to 1 index less than that, and so while j is greater than 0 and my list is, or the number you're looking at index j is greater than x, you're then just going to keep trying to move it into its right place over and over and swapping it down the list. Okay, and so this is the part that we were looking at here. This kind of orange bump down the list is the loop over j that we have on the inside there. Okay, and so all it's saying is that just look to your left, so into that sorted sublist, and then you're going to keep looping down the sorted sublist until you find the correct place where it needs to go, or you've just hit the edge. And if you hit the edge, then you need to go and just put you've found the minimum value, and you need to go and put it into that index. Otherwise, the second condition will fail, and so you know that you've now reached the correct place to put value x. Okay, and so once you reach the second one, then obviously the current value at index j is going to be greater than or equal to x, and so you can just stop. Once you found that point, you just slot x in where it needs to go. Okay, and so in the algorithm, as much as I've shown it here as a bunch of steps, it is 2, so j minus 1 will start off there, and you'll say, is j kind of at index 0? It's not. Is x, which would be 2, greater than 11? It is, or sorry, less than 11? It is, and so you're going to swap it. And so 2 would go there, and 11 goes there. And then you keep looping down j. Alright, so now j would be pointing here, and so is this value greater than 2? It is, and so you're going to swap it. And swap it, and swap it, and swap it. Right, until the index fails. In which case it would be here where is 1, j minus 1 be pointing there. And so you then say, is 1 less than 2? It's not. So 2 stays where it is. Is 1 greater than 2? It's not. So 2 stays there. Okay, so this is the, just to be clear, j then is the loop into the sorted sublist, and then the outer loop is just finding where to stick x. Okay, so is this complete? Yes, it will return a sorted sublist regardless of the instantiation, and eventually that sublist will become the full list, so it will return the full list regardless of instantiation. In the best case, however, it's not going to loop at all. Alright, so this condition will fail every single time, but in the worst case, it's going to have to loop all the way back to the end every single time. So there is going to be some cases, and we're just going to look in terms of the comparisons, right? So essentially the evaluations of this condition here. Okay, so because the sublist is sorted, we just need to check the last value with the new value to see if it's even needed to look over the sorted sublist. So what I'm saying here is that if I want to know whether or not I even need to scan into the sublist, all I need to do is this one comparison here. And that's the benefit of knowing that everything to this left side is the sorted sublist. And fundamentally, this is why it's called the decrease and conquer, right? Is because you are decreasing the problem every single time, but in a way that gives you information that you can use as like a quick check on the next time, right? So I don't need to go and do this scan the whole time. I can tell from the first comparison whether it's ever necessary to do the scan. Okay, and so that helps a bunch because now you can only, in the best case, you just see that you never need to scan. Alright, and this happens when the list is already in ascending order. Okay, and so we can just go through the slides. So because the sublist is sorted, I'm just going to read through here. We just need to check the last value with the new value to see if it is even needed to look through it. So again, the new value here would be x, and the last value is the j-1 index, so the last index of the sorted sublist. So in the best case, you just never need to search into the sublist, and this would happen when the list is already in ascending order. In that case, x will always be greater than the last value we've been able to put into the sublist, and so we'll always see false on that first loop down into the sorted sublist, and so we'll always then just break out or just know that x is in its right place. However, in the worst case, we have to search over the whole sublist and look over all of it every single time. Okay, so there's never a case where we only go a couple down. All of these arrows, all of these orange arrows, let's find one, it works. No, it's not set up super clearly, but like here, we didn't have to go and swap 3 and 1, and so there was a little bit of benefit here. But in the worst case scenario, I have to move the value all the way down every single time. And so that's going to happen when my list is already in descending order. Okay, so if the list is in descending order, I have to do 2 full sweeps of n, right, each time, just to try and get the correct value into its right place. And this essentially then starts to look a lot like a selection sort again. Right, so you're then always just kind of going and selecting and putting it where it needs to go, and you're back to that order n squared complexity. And so by maintaining a sorted sublist, we give ourselves information for the inner loop that we can leverage to get a better best case complexity. Alright, so it's all just about maintaining that little bit of knowledge, which allows you to then have a kind of breakout condition. Is it optimal? Well, it's correct. Alright, so step 1 of our optimality proof is good there, but it's still order n squared in the worst case complexity. Alright, so 1 outer loop for handling each value, 1 inner loop for moving specific value to the right place, and then in the worst case, this moves the value to the end of the list each time. Alright, as we said, the worst case complexity. So it's not optimal, as a better worst case complexity does exist for comparisons, and again, we'll see that in a bit. So order n squared, worst case, even though the insertion sort had a really good best case complexity, the worst case complexity is still not great. So, well, it still could be lower in terms of the problem definition, and so it's not optimal. But you may then be asking, you've heard insertion sorts is really popular, why is that the case? And that's because it's extremely efficient when it's not dealing with its worst case scenario, which is quite common, right? Especially with really large lists. It's very uncommon you'll get a list that is actually in descending order to start with, and so you can actually very likely end up in a case where you're getting kind of decent efficiency, and the average complexity is actually looking a little bit more reasonable, even though the worst case is quite bad. So it's great to have optimality and all, but it should be weighed with the practicalities of the problem, and insertion sorts in practice does really well because it has this really good best case complexity, alright, because it has this order n that it can often find and fall back to. Okay, looking at the next algorithm, so there's the merge sort. So this is now our first divide and conquer algorithm. So it is a recursive procedure, hence the divide aspect. And so you're going to split the list into 2, dividing it, and then you're just going to conquer, you're going to do the sort on the left and right sublists. Okay, and then from there you're going to then merge the 2 sorted sublists. So here's the pseudocode. So you're given inputs. In this case, you're just going to assume you have left and right indices that go into the array my list of n entries. So a little bit inconsistent in that definition in the past we were having my list and then entries. But in this case, we just need to kind of maintain the indices themselves to kind of go and index into my list. And so the output is and also that just note that this is because it's recursive, right? So you could obviously write it in a way where you're passing that along, but in this doing it this way, you're recursive in this call, but it's all indexing into this like global mylist variable, which is why this algorithm is written this way. It's not a mistake or anything. It's just because you assume you have this global mylist array with n entries, and so as you do these recursive calls, they're all still indexing into the global array, just with different start and end points in terms of left and right. Okay, and so the output is going to be a portion of the array minus, so again, portion because it's recursive, because we haven't, passed in new values, or new copies. So where the values in my list are such that it's going to be sorted between left and right. Okay, so all one call of this algorithm is really caring about is the fact that the sub portion of it that it's looking at between left and right is now sorted. There's an escape condition just to make sure we don't do silly things and loop forever. And we're going to say if right is less than left, we can keep going. Otherwise, we've crossed a point where obviously it doesn't make sense anymore and we need to break out. All right, and so once right and left are equal, that's, we're going to get a case where this is negative, but once right and left are equal, then obviously you've reached an array of size 1, which we know is sorted. Okay, and so we can then break out from there. But if this isn't true yet, then it means we have an array that could need sorting, and so we're just going to split it in half. Okay, so you're just going to find the midpoint of this array, and then say merge what's to the left, merge what's to the right. Okay, by assumption here, we just go mid is to the part of the left, and then mid plus 1 goes to the right. And then, importantly, you get back 2 solutions from this, where you've now achieved this effect of sorting the sublists, and so now you just need to merge them. Alright, so in this case you need to track where all the indices are. So all the different start and end points, obviously mid and mid plus 1 could have been collapsed, but for argument's sake we now need to just merge these two things together. Okay, so really you can see that a lot of the work is just doing the division, but then the actual complexity, the actual work gets done in this merge case. Alright. So the crux of the algorithm is the merge. Okay, so you're given 2 sorted sublists. All you have to do is combine them into 1 sorted list. Alright, so again here, you know that everything between left and mid is sorted. You know that everything between mid plus 1 and right is sorted. And you know that they are actually, arrays greater than 1 if you're now needing to merge them back together. Otherwise, you got to a point where you just had an array of size 1 and you just return it, and so you just would kind of pop that back up, right? So these 2 calls here could be of size 1, but that means that this overall loop is doing something on a list that could be size 2, and so now you need to combine those 2 one index arrays, or obviously they could be larger. Okay, but just to be clear how this fits in, you would terminate when you're on a list of size 1, and then that would pull through back up into your 2 outputs here, or into your 2 kind of sorted sublists here, and then you just learn how to combine them. We'll see how to combine them. Okay, so this can be done in linear time because your sublists are sorted, which is why this is so powerful. So merging them together can be done in linear time. So let's assume we have our left and right sublists as follows. So we've sorted the left sublist, we've sorted the right sublist. 21, 29, and 99 are in ascending order. 10, 42, and 92 are in ascending order. And so all we have to do now is merge them. Right? And so we know that this was our call to the left. We know that this was our call to the right. Can we put them back together? And so this is what's going to happen. You're going to copy it into this temp space. And so there is this now memory, additional memory that's needed. Some algorithms, and for this example, you reverse them just for consistency. I did this way. You don't obviously have to. You could just do the indices differently. But for argument's sake, this algorithm reverses it. So you have 21, 29, and 99. That just goes in straight on the left. And then the reverse of your list on the right gets appended to it. So you have 10, 42, 92 reading from right to left. And you're going to start your pointers, one on the left side, one on the right side. And you're now just going to look for the values that are smaller so that you can put them into the right place. Okay, so 10, It's less than 21, so it goes into the first index of the sorted array. Okay, then you're going to move it over and you're going to look at 42 compared to 21. 21 goes in. You're going to move that index over. 29 versus 42, 29 goes in the right place. Then 42 goes in, then 92, then 99. And so you're just scanning the one pointer from left to right in its left sublist, and the one pointer from right to left in the right sublist, looking for values. And because you know that they're ordered, you know that the comparison, only one of them is needed at a time. You're not going to find a smaller value that should go in earlier if you're already looking at 21 and 10, right? You're looking at the two smallest possible values in the array because they are the minimum of their two independent sublists. So it's just a case of, I know that everything else is ordered, so I just need to go and look at the minimum on the left, minimum on the right, and see what then is the minimum overall. Okay, so here's another example, just from the start. So we're going to start with our subleft, our full list. So you say left is 0, right is n minus 1, so in this case n is 8, so 7. And we're going to find our midpoint, so you add them two together, divide by 2 and take the floor. Okay, so 7 divided by 2, 3.5, take the floor gives us 3. And then that's our split point. Okay, we split it like that. There's our variables. We now have our new left and right terms, and our new left and right terms for our sub call. Right, so these are the two new calls to the merge sort. You get their mid values, and you split, and so on, and eventually you end up in our termination condition. Alright, so in this case, left and right would both be pointing to the same value of 0, so that minus now, it's not greater than 0, and so you end up returning these values back. Okay, this is a sorted sublist, that's a sorted sublist, and so on. So now you're going to initialize your values, I and j. Again, we can reverse them, we cannot, and this obviously doesn't need to be reversed. So you just say, is I less than j? It's not, and so you're going to stick the value of 1 in there. And another good thing to know is that once this index moves out of range, you know that you can then just copy all that's left in the subproblem that remains into its correct position. So 3 is going to come down in here. And that's because j is now gone past the end of the array, so it's already allocated all of its values. And so the 3 goes in there, and again, you don't have to do it that way, but you can then just have said copy everything because j went out of range. Going to do the same thing for all of the other subproblems. You just put them back up, and again, this operates the same as like a recursive. Well, it is a recursive call, so this is happening independently to all of the i's and j's. So we don't care about all the other ones. These are new function calls each time. So now we have the output of our earlier call to the left subproblem here and the right subproblem there. Same, this is an earlier left subproblem and an earlier right subproblem. So now we just need to combine these two and combine these two. How do we do that? In this example, I'm not reversing the order. Again, you could have, and you would just start with j on the right hand side and loop to the left. In this case, I'm just starting with j on the left hand side and looping to the right. So is 1 less than 2? It is, so you copy the I and move its index across. Is 3 less than 2? It is not, so you copy j's value and move it one item up. Is 3 less than 19? Obviously no. Copy 3 and you copy the 19. Then you can check that you get the same output on the right hand side here. Okay, so now you have the left subproblem and the right subproblem that have been sorted from the original call to merge sort, and so all that's left is to combine them. Alright, and so you can go and check this one yourself if you'd like, but again, you're just going to initialize on the left here and on the right over there. Scan through comparing, scan through comparing, and you just find the smallest values each time. So the first 3 values here, so I would start there, and j would start at 4, so I would be 1 compared to 4, 1 is smaller. Then I would move over, 2 less than 4, 2 would go there, I would move over, 3 is less than 4, it is, so it gets copied, I would move over. And so you're already pointing at 19 here, and then you finally find 19 less than 4, it's not, so you copy 4 over and it starts iterating up. Okay. What are the properties of the merge sort? It is correct, and again, you can do this by induction. So you can show this in pieces. First, you would prove that the merge is always correct, and then you show that the whole algorithm using the merge is correct. So because there is this kind of one very clear place, or sub algorithm, you would first show that the sub algorithm is correct, and then what does that mean for how it incorporates or kind of gets included into the kind of combining or the splitting and then combining. How is the complexity? Well, merge sort does the same thing regardless of the input, so it is a recursive algorithm, and that then allows us to make this a recursive equation. So I just want to make this really clear now because you're going to see this again in the tutorials, but it helps to see the concept of this. Alright, so you first split the list in half, sort both halves, and then merge. Alright, so if we're looking for the complexity of the algorithm as a whole, you can call, because it's a recursive complexity on the algorithm, this becomes a recursive equation. Alright, so what I mean by this is that you can see to get the complexity for size n, so g of n, that's the same as splitting and then sorting both halves. So you have two halves, and they're now doing the same complexity, but on half the size arrays, just two of them. And then there's the merge step, which is just added at the end. Alright, and this merge step we just showed you is linear. So that's just order n, so that takes n steps. G of n we don't kind of fully know yet, that's the full complexity, and we just kind of have to keep track of that G of n function. And so ultimately, we say that G of n is an element of big O n log n, because eventually we will then find that we have a limiting case on G of n, and that is how eventually you break out of this recursive equation, right? The limiting case is when the left and right pointers are pointing to the same index, in which case G of n becomes a constant complexity, and so you'll then know how many splits you can do on an array to get to that point, and you can do log n of them, alright? Or log base 2 of them, right? How many times can you split an array of size n in half? Log base 2 of that n you can split in half. Well, again, we'll look at it in the tutorial. But you keep splitting it in half as many times as you need to, and eventually you just get to a constant value, right? So that's just order 1. So that's why that's not even showing up in here, is because when you reach the limiting case, you actually hit a constant time complexity of just saying, well, I have nothing to do here, I'm going to return. So then the question is, how many times did I do a split that required n merges? And that is what this n of log, or this log n multiple is doing here. It's not the complexity of checking the whether or not you need to keep splitting. That ends up being constant. It's how many times did I do this split operation requiring n recombinations. Okay, and there's a little bit more detailed how you get n there, because you end up doing n every time because there's a left and a right part. So it's every split is recombined with n comparisons and so on. We'll go through that in the when we look at this, but it is just important to know that that log n multiple is coming from the number of splits we do, not necessarily from the actual work done in that limiting case. And you can see that here. So every time I then do a call, it's a new recursive call. So this was the first split, but then that requires two merge operations on another two merge operations on the quarter side, and then that's plus n over 2. Okay, I think that should this be 4? I can't remember. Oh, no, obviously not, because this is the one sub problem. Alright, so that's the one sub call. So you then just get 2 quarters for one of the halves, and then there's the quarter size, and then the recombination is now just of one of the sides, and you have to do that twice. So obviously that's 2, because that's just a new split in half. That gives you quarter size, and you have to then merge back up, which is a number of merges of the half, and then that pulls out front. So you have to do this on 4 quarters, and then keep merging. As you can see, every time you do a merge, you pull out an n. So I did 2 splits from full into half into quarter. So 2 splits, each one gave me an n out front. And so how many splits do I do? Times by the number of combinations there. Okay, and so this leads to the final complexity of order n log n. So the one thing to take away from here, again, every time I split, I get a recombination of size n, and then we just kind of keep track how many times until I reach a constant complexity here, which is in the limiting case. And so we know the limiting case is when I've split all the way down to size of 1, which will be log n. And so we finally have a kind of worst case complexity that is order n log n, right? So all the algorithms up to now have been worst case complexity order n squared. We did obviously have insertion sort, which had a best case complexity of order n, but insertion sort still had order n squared worst case complexity. In this case, merge sort does not have best and worst cases, so the best case is actually worse than insertion sort, but it has a better worst case complexity. And so now let's see what the consequences are. And so there are some trade-offs. It does need to create a copy of the data in the merge step, so it is order n memory still, but does actually double the amount of memory you need. And so either this is by putting the two lists together with the second in reverse, or by tracking the two halves into a copied larger list. So the two ways you can do it. That we saw examples of both. And then there's the order n log n complexity is fixed. It's not just in worst case. So insertion sort has a better best case complexity of order n. And so when should we use either? That's the big trade-off here. There's a decision to be made. And so usually you would use insertion sort when the inputs are likely to be quite varied. You know that it's very random. You're not going to encounter your worst case scenario often. You can kind of use a little bit of the domain knowledge to say worst case is unlikely, especially given large n. Whereas merge sort you can use when the cost of suboptimality on a single instance is high, right? So in this case, if you're going to be really suboptimal on an instance, then you don't want the cost of that to be high. And so merge sort just guarantees you that you're never going to run into this really, really large cost that you have to cover, right? This may be detrimental, this very detrimental kind of instance that you don't want to ever encounter. Whereas insertion sort, yes, you're probably better in the best case, but it can be very costly if you run into that worst case scenario. Okay, so again, I think the important thing to take away from a lot of these is there's no right answer. Usually it depends on your ability to understand a set of algorithms, treat them as tools in a toolbox, and then know when, given the domain, given the problem setting that you're in, when is the appropriate time to use either one. Okay, and I really do like this discussion around insertion versus merge sort in terms of their best and worst case complexity, because it, number one, it also shows insight into your understanding of optimality and things like that, because now the merge sort is optimal, but it also shows that like there is a better base case, and sometimes that's the thing that we can use to determine the algorithm we use. So you pick an algorithm that is not optimal, leaning on the fact that it has a better best case, when I don't mind having a really bad worst case, once in a very long while. Okay, then the last algorithm we're going to look at is the quicksort. So in this case, you're going to select a value in the list and you're going to call it a pivot. And then all we're going to do is try and put the pivot in its correct place. We're then going to guarantee that elements to the left of the pivot are smaller than this number and to the right are larger. In other words, the pivot, similar to some of the other algorithms, is always going to be in its correct final spot. However, in this case, we're going to make no claims about the values to the left and the right, aside from the fact that they're smaller and larger respectively. So they are not necessarily sorted or even balanced. So it's a really kind of sloppy-ish algorithm in that regard. So you are then going to recursively sort the left and right sublists. So this is another divide and conquer algorithm. So again, we're not passing in my list, we're working on the indices of my list, which is of size n. Okay, and all the algorithm cares about is making sure that the indices, the values between its two bounding indices, left and right, are sorted by the end of it. Okay, similar story, is right greater than left. The previous algorithm said is right minus left greater than 0. Same thing, obviously, in this case, you just pull it over the greater than sign. If so, well, if not, then you know you have a list of size 1 and you stop and you reach the limited case. If this is still true, then we need to divide and conquer. So you're going to just pick the value that helps you partition the problem. Alright, so you're going to say, how do I, given indices left and right, how do I aim to partition the array? And this partition choice is where a lot of the problem lies then. Similar to the strategy for merging in the merge sort, picking the partition point is the big kind of crux of this algorithm. Then all you're going to do is call quicksort again on the left and the right problems. Alright, so let's look at the partition algorithm. So you're going to usually just say that you're going to select my list right as the element that will be moved to the correct place at the end. So this is your partition. You just pick the furthest value to the right and rely on that and decide that you're going to move it to its correct place. There are other ways to pick. You can pick randomly if you want. It all works. It's quite flexible in that regard, but this is kind of a standard that everyone seems to just have kind of agreed on, because when making an arbitrary choice, what's best is usually just consistency. And so once you've picked your pivot, you're then just going to scan from the left until every element is greater than the my list on the right. Sorry, you're going to scan from the left until an element that is greater than the value on the right is found. Once that happens, you're going to start scanning from the right hand side, so until you find an element that is less than the element on the right. So the fact that it's less than and not equal is, you will then scan past the current value that's there. It's not like you're going to get stuck. If this was equal, then you would obviously get stuck. You could also just be a little bit clever and start this scan on the right from one index to the left of your right value. Same kind of thing. It doesn't really impact the complexity, but you can be slightly smarter about it. Whereas from the left, you're looking for values that are greater than or equal to what's on the right. You're in the list on the right. Okay, so you're scanning from the left, you're trying to find a greater value, and then once you do, you start scanning from the right, you start looking for a lesser value. This is important because a lot of our cases are dependent on the fact that these are in order. That first I've found a value greater, and then I've found a value smaller. And this does kind of come up in the case analysis and how we understand why this works. Once this has happened, where you found a left and a right value that fit these conditions, then you swap them. Why does this help me? Well, now I know that I've put a value that is greater than what was on the right up in the list, and a value that was smaller is now down in the list, which means that ultimately I'm not going to get stuck in the same position, and so I can keep looking, and somewhere between where I did these swaps is where the right value should go. Okay, and you continue until left and right pointers cross. This is then the limiting case in the algorithm. When they cross, then left and right subtracted is 0, or right is less than left. Once you do this, once they cross, it means that the crossing point is where this value that was on the right should go, and you just stick it where the left pointer is pointing. So here's the intuition. So where the two pointers cross is where the pivots should go. And so in that case, all numbers to the left of the cross will, by definition, be smaller than the pivot, or else you wouldn't have been able to keep iterating past it. So it would not have gone past them. And all numbers to the right of that crossing point will be larger than the pivot, or else again, that right pointer would not have been able to go past it. And that's the kind of key point, right? Is because we're looking on the left for values that are larger, and we're looking on the right for values that are smaller. Once we swap them, they then fit each other's condition. Alright, now where that pointer on the left is looking, it now has a value that's lesser, and so it can keep iterating. Same for the point on the right, it found a value that was smaller than the pivot, and so it got swapped, and now it has a value that's larger than the pivot, in which case its condition is met and it can keep iterating down. And so because their conditions then always met, if they've crossed, it means they're no longer in this like contradictory point, and so you can now know exactly where to put your pivot. Okay, and so the crossing point will be where the left pointer stopped, which has two cases. Either the left pointer, and again, this is what I mean when I say that our understanding of the algorithm depends on the fact that this is ordered, right? Because we know that left will stop before right, we can now break it down into some cases depending just on how the left pointer stops. So the crossing point will be the left pointer stopped by definition that happened first, which has two cases, either a number larger than the pivot, either we found a number that was larger than the pivot and can go to the end when swapping without breaking our condition, or we found the pivot ourselves. Alright, so when the pivot is in the right place already. So either we kept going and we eventually got a right value that needs to be swapped out, or the pivots, we never found the right value, but then the pivot can keep. The pivot needs to, we eventually iterate, sorry, let me redo this. So the crossing point will be where the left pointer stopped, which has two cases. Either that it reached a condition where it halted because it found a value that was larger than the pivot, and so it needs to then, that value needs to swap down the list, or there is a case where it just keeps going and then eventually hits the right hand side. Okay, so it never actually fails its condition, and so it just keeps going all the way to the right. In which case, it means that we will eventually bump into the pivot itself, and so there's no swap that's needed. Okay, and so another way of looking at this, and this is then why the left pointer tells us exactly where it needs to go. Okay, if you've crossed, then either you've crossed in a case where the right value kept iterating down after that, and so you know where to put it, or the left value just says the right pointer is already in its correct place. So this left pointer serves a dual role. It says, do I need to move the right pointer or not? Or do I need to move the pivot or not? There's another way to look at this, which breaks down into three cases, which I think I find a little bit more intuitive, is that either the left and right pointers both stopped somewhere, but they did not cross, in which case we found two numbers that can be swapped and we can keep iterating. Okay, we found two values which contradict their rule about being left or right of the pointer of the pivot, but if we swap them, we just get back to satisfying their conditions and we can keep going. All the left pointers stopped, but the right pointer did not, and then this resulted in the cross, in which case one of them is contradicting, the other is not. Alright, and so what this means is that there was no number lower than the pivot to the right of the crossing point, and so you must have found exactly where the pivot should go. Okay, so if the left pointer stopped, it means that it found a value that is greater than the pivot, but there was no way that I could reconcile this by looking anywhere to the right of that, except by moving the pivot into that position itself. Okay, so again, we're just looking for ways of reconciling what's on the left and the right. And so my first preference is to find a contradicting point on the right that isn't the pivot and then just swap them, because that allows me to keep going. Alright, but if my left pointer stops and my right pointer does not, it means that there's a contradiction. I found a point that is to the left of that pivot, or kind of where the pivot currently is, that should be greater than it, but there's no way of reconciling it by picking any number to the right hand side. So for example, all numbers to the right of that point satisfy the condition that they are larger than the pivot. And so if I then just move the pivot to where that left pointer is pointing, I will then have put the larger value in the left pointer all the way to the end, and the pivot is in the correct place. And so I now no longer have a contradiction. I just now need to go and start picking a new pivot. Alright, because I've now moved my pivot. Or the third case is that the left pointer did not stop, in which case it will actually reach the pivot point itself, and so you never find any contradicting value. You never see anything that says, I find a value on the left that is greater than my pivot, and so all values to the left of where your pivot currently is at the end of the array will then need to be moved, or do not need to be moved, and so your pivot is actually in the correct place. Okay? And so here's an example we can look at to try and make it concrete, and then I urge you to go back and look at these intuition steps again. And so initially we're going to start with this array. So we have our left and our right pointers, and the pivot is 8, right? So obviously j is going to move past 8 because it is not greater than itself. But we're going to start by looping on the left. We're going to say, is this value at index I greater than 8? And it's 7, so it's not. So we're going to keep shifting. Is 12 greater than 8? It is, and so we found a contradiction. Alright, or this hypothetical contradiction. We're saying that everything in this index I should be less than what's in the pivot, and so now we need to resolve this contradiction. So now what we're going to do is we're going to start scanning down from the right to see if there's anything that could tell us that we could use to resolve the contradiction. Okay, so is j less than 8, where it's currently pointing at 4, and that's true. And so this is great. We've just found two values. They both contradict. J should be greater, I should be lesser. But if I swap them, those two conditions are met, and I can go back to iterating over both of them. So I swap, and I move my index I one up. Okay, so is I the current value of I greater than 8? It's not, so you keep going, you keep going, you keep going, and eventually you get to an index I that is now greater. And so you're going to go back to J and say, well, can I find anything that works? J was kind of where it was, should have been from last time, so you're going to start by just shifting it down. And so now you're at this point where right and left are not different. Right minus left is not greater than 0, or right is equal to left. And so now you've found a point where there's a contradiction. I's pointer should always be less than your pivot, but there's nothing I have on the right hand side to fix it, and so the only thing on the right hand side that I can use to actually fix this condition is to move the pivot itself. And so the pivot goes into its right place. Some algorithms say that j and I mustn't cross or whatever, but I would just say when they're equal, it's fine as well. Okay, because again, j is then going to just move past, but I is the one you care about anyway. And so the pivot goes into its right place. And so now you've got 8 in its correct place. And so all you have to do is now split into your left and right sublists and keep doing the same algorithm over and over and over. Okay, so now you have your pivot over here, which is 6, right? The end value of your left subproblem. You're going to start looping. So is 7 greater than 6? It is, so you've got a contradiction immediately. Is 2 less than 6? It is, so you've got the contradiction for the j pointer immediately. We can just swap them and carry on going. Then is 4 greater than 6? It's not. 5 is not greater than 6. And your pointers meet again, so is 7 greater than 6? It is. You keep going, and now they're equal. The j has moved past. In which case, you've got a contradiction on I. It's now greater than 6, but the j pivot didn't find anything on the right hand side to resolve it. And sorry, the j index didn't find anything to resolve it. So the only thing to the right of I that we can use to fix this problem is for 6 to go into where 7 is. Alright, and so in this case you now have a sorted sublist. This is, however, the worst case. You can see why the worst case happens here for this sublist here. Not the overall problem. For the sublist, this is the worst case. What just happened is that we only reduced the length of the list by 1. Alright? And so we split off the 7, but the 6 was already there. Alright? And so we haven't really done much in terms of actually solving these problems, aside from just moving one index into its correct place, or the pivot ultimately only moved one step over. What we really want is the pivots to come into the middle, so we get a subproblem on the left and the right that are small. But in this case, it was a small swap. The pivot only moved one index over, and so we only gained kind of the benefit of one index there. So this only happens because our pivot was also the max, or the second max in this case. Same kind of story. If it was the max, then it would have just kind of split off to the left. So they're both kind of equivalent if it's the max or the second max there. In other words, it was already in its correct position, so a sorted list is the worst case for quicksort. Alright, or equivalent to the worst case for quicksort. I will just make sure that that's a little bit more precise to the fact that that was 6 and not 7, being the pivot. Okay, so we know then that quicksort has a pretty bad worst case complexity. So what are its properties? Well, it is correct. It will always return a sorted sublist. Let's just pop all these in. So complexity, the partition step is linear. It obviously just has to scan through and find the kind of correct place to stick that pivot. So that is the linear part of the solution. and then it has to sort the left and right sublists. Okay, so in the best case, when our partitioning divides the list exactly in half every time, right? So you do this linear scan, and you end up with a left sublist and a right sublist that are balanced, and then you just have to do that scan part of the computation, which gives us g of n, right? So it's once again order n log, sorry, which gives us the g of n is order n log n. So how many times can I split the problem in half before I reach a limiting case? Log base 2 of n, okay, and then every time I do that split, I have to do an n scan of the array to find the pivot point, and so that gives us n multiples of log n. Okay, in the worst case though, when the list is completely unbalanced each time, and so it's already sorted, and so your pivot is always on the right and it never moves, well, then the complexity of sorting the right is constant, right? It's just a list of size 0, so you reach the limiting case, but then you're left with the complexity of always doing this operation on n minus 1 length, and each time it's going to cost you n to do that partitioning step, okay? And so now you're going to end up doing n work, and you only benefit by one step, and you have to do n minus 1 work again, and then n minus 2 work again, and n minus 3 work again, because every time you're always splitting off this constant complexity here that does nothing. Alright, that's no work, but you're not really decreasing it a lot. And so in that case, you end up with n plus n minus 1 plus n minus 2 plus n minus 3, which is once again that kind of arithmetic sequence equation that we have. So is this optimal? It is correct, but the worst case complexity is not as good as the merge sort, so it is suboptimal. Well, not suboptimal, so it is not optimal. But then again, you may be wondering, why is quicksort so popular? Well, because modern algorithms typically use sorting algorithms based off of a combination of quicksort and insertion sort. So there are hybrid methods. You kind of hear about this a lot. In fact, both of them you hear about a lot because they're used together in combination, but also because quicksort benefits from something other than just optimality, which is the fact that it has cache locality. Okay, and so because it does a linear scan and inline replacement, it benefits from the fact that memory is loaded in chunks, and so it's very likely that the next value you need is already sitting in the cache. Okay, each time you loop over, you benefit from the fact that you're doing this sequentially. Whereas something like heap sort, which we're not going to study, but it's another sorting algorithm, has really bad locality even though it's optimal. And merge sort copies your data into a second array, which also limits its locality. So even though it's also optimal, it then doesn't benefit from the same cache locality. So this all makes quicksort practically very useful in a very similar way to something like insertion sort. Okay, so again, we may be studying the analysis of these algorithms, but a lot of times it has to be paired with something a little bit more practical and fundamental. So let's go through some conclusions. We looked at non-optimal sorting algorithms such as the selection, bubble sort, and even something like insertion sort. We looked at the divide and conquer algorithms, so then these were the merge sort and quick sort. Obviously max sort in this case is just similar to the selection sort. Order n log n is optimal for the comparison sorts. Again, this is based on worst case complexity. However, in practice, merge sort and quick sort are both good candidates, even though they are not optimal. Sorry, merge sort is optimal. Quick sort and insertion sort are decent candidates, even though they are not optimal. Merge sort is optimal and also used in practice. Insertion sort is usually good for small lists, and since it has good best case behavior, you can often risk a bad worst case when the list is small, or if it's really large and you know that it's unlikely. So it depends on the domain knowledge there. And yeah, eventually in your honors algorithms class, you can look at hybrid sorting approaches, which then work quite well together. All right, thanks everyone. I know there was kind of like a whip through of sorting algorithms. We will be, using this to do a little bit more theory in the tutorials, and we'll go through into some of the more derivations in detail with a bit more precision. But again, I think the main things to take away from this lecture is these trade-offs. It's whether or not something is optimal, whether or not something is good in the worst case, whether or not something's good in the bad case. whether or not something has practical considerations to take into account. For example, the cache locality example, and then lastly, how does the choice of metric factor into the analysis, right? So even in something as simple as selection sort, did I count based on swaps? Did I count based on comparisons? And so on. How does that change the analysis? Okay. All right. Thanks, everyone. And then I'll see you in person again next week. Let's get this one.